A black hole represents the ultimate cosmic dead end. The gravity is so intense that any matter or light that crosses the threshold is permanently trapped and crushed out of existence. But the equations of general relativity that predicted these gravity wells contain a bizarre mathematical twist. In 1960, physics dictate a white hole. It is defined by an event horizon you can only fall out of, a one-way cosmic exit door that violently spews matter and light into space. For decades, physicists dismissed these objects as mathematical trash. The equations allowed for them, but researchers assumed they were highly unstable anomalies that could never actually form in the real universe. Today, the scientific consensus has entirely shifted. Physicists are actively hunting for white holes, because these theoretical objects might be the only way to resolve a glaring flaw in modern physics. The problem stems from Stephen Hawking's information paradox. He demonstrated that as a black hole slowly evaporates over time, the quantum information of everything that fell into it appears to be permanently destroyed. That total destruction violates the absolute core laws of quantum mechanics, which state that information cannot be lost. If a black hole really deletes the physical record of what it consumed, our two best models of reality directly contradict each other. Theoretical physicist Carlo Rovelli and his colleagues have proposed a mechanism to save that lost information, relying on a framework called loop quantum gravity. Under this framework, when a dying star collapses at the bottom of a black hole, it does not shrink down into a point of infinite density. Instead, the collapse hits a hard physical limit, the Planck scale. At this rigid limit, extreme quantum pressure forces the collapsed star to rebound. The matter bounces inside out in a quantum bounce, forcing the black hole to transition entirely into a white hole. If they bounce immediately, why haven't we seen them erupting everywhere? The answer is extreme time dilation. To the matter undergoing the bounce, it takes a fraction of a second. To an outside observer watching that intense gravity well, that fraction of a second stretches out over billions of years. A white hole acts as the delayed cosmic afterlife of a black hole. It preserves all the devoured quantum information and, after billions of years, finally ejects it back into the universe. We might already be observing these macroscopic white hole explosions without realizing it. Astronomers regularly detect gamma-ray bursts, intense flashes of energy usually tied to the explosion of a dying star. But a specific subset of these bursts lacks any trace of a supernova signature. These strange, isolated bursts spontaneously erupt and eject massive amounts of matter and energy from apparent empty voids in space. Theoretical models label these events small bangs. Definitively identifying one of these anomalous bursts as a white hole would prove that the universe recycles its most extreme dead objects. To find empirical evidence, physicists are looking back to the early universe. Tiny primordial black holes formed shortly after the Big Bang would experience a much shorter time dilation, meaning their quantum bounce should be reaching our detectors right now. The first detection method relies on the upcoming LISA space observatory. It is designed to hunt for a stochastic gravitational wave background, an ambient ripple in spacetime produced by thousands of these primordial objects bouncing simultaneously. This chart shows the exact signature LISA is looking for. The white hole contribution to the gravitational wave background should appear as a low-frequency hum that remains constant before sharply decaying at exactly the 10 MHz frequency mark. The second detection method uses the cosmic microwave background. Experiments like CMB-S4 scan the ancient light of the universe to find large-scale polarization anomalies known as B-modes. This chart shows the specific predictive target in the CMB data. White hole metric perturbations should manifest as a massive density spike peaking perfectly in alignment with the L equals 200 multipole line, distinguishing them from standard cosmic inflation. This chart shows the joint detection model. Researchers must cross-reference LISA's gravitational wave data with CMB-S4's B-mode polarization to reach this high-probability yellow zone in the upper right. Achieving a high-probability joint detection across both independent datasets is crucial because it rules out instrumental noise and other random cosmological sources. The search for these intersecting signals serves a higher purpose than simply adding a bizarre celestial body to our astronomical catalogs. Discovering these dual signals would provide humanity with the first direct empirical proof of quantum gravity at work on a cosmological scale. Confirming the existence of white holes resolves the conflict between our physical laws and proves that nothing in the universe is truly lost forever, not even in the darkest depths of a black hole.